All right, so here are the electrical symbol. Okay. Okay, so this is a resistor, and I have a switch. Okay. And what I'm going to do is I'm going to close the switch. Right now, current in this thing is 0. And when I close the switch, the current in this circuit will rise instantly. So here's the current, here's time. At time t equal to 0, I'll close the switch. So before 0, the current is 0. And then at t equal to 0, I will close the switch and the current will instantly go to its value, I equal to V by R. Okay. Now here's the deal. So now what we're going to show to you is, so if you place an inductor, so this, by the way, what I've been said is this is an ideal inductor. It has no resistance, but anyway, so we'll talk about ideal things. Okay. So now in this circuit, so the only thing that has changed is I've introduced this inductor. And now if I close the switch at t equal to 0, okay, so before I close the switch, the current was 0. And at t equal to 0, I close the switch. And now the current will rise like this. Okay, so it'll go to its same steady state value, V by R, except that it takes a little while to go do that. And this could be depending on, so the time constant is L by R. And typically this takes, let's say 50 to 100 milliseconds, depending on, of course, the time constant. So that is what we are going to talk about. So we are interested in a phenomenon, so this slow rise in current. And when we say slow, we're talking about 50 to 100 milliseconds. Okay. And I mean, this stuff matters. So for instance, I mean, if instead this was, let's say 2 hours, then maybe this kind of communication would not be possible, because if you had that kind of delay, you wouldn't get instantaneous response. When I write here, you're seeing across hundreds of miles, you're seeing it instantly. Okay. So I mean that's sort of a, I mean, an example I sort of cooked up, but you know, we are interested in these phenomena that are delayed by milliseconds. Okay, so that's the idea. Okay, so you guys understand what is happening when you introduce this inductor? Remember, this inductor fights changes in current. So when you close this switch, as the current was trying to increase, this was fighting that change, and that's why the current had to rise slowly. Okay, that's why the current rose slowly. So let me actually show you this thing. Okay. So let's first decrease the inductance. Okay, so here's the battery, here's the resistance, here's the inductor. And I will close the switch. So if this inductor wasn't present, the instant I close the switch, the current would be a step function. It would be, the current would be like this. The current would rise like this. Okay, it would instantly rise to its value. But because of the inductor present, it will rise like so. Okay, so let's close the switch. And you see there is the inductor rising like that. Okay. And the time constant for this circuit was 1 millisecond. So in about 3 milliseconds, it's gone to its steady state value. So all this happened in a flash. 3 milliseconds is a blink of an eye. But this kind of stuff matters to us. So that's why we're studying it. Okay. Now let me increase the value of the inductance. Okay. And the current rises more slowly. Okay. Now the time constant is 2 milliseconds. So in about 6 milliseconds, it's gone to it. So let's say, okay, so 5 milliseconds and so on. Okay, so you can see that. All right, so we are talking about phenomena that happen over the span of milliseconds, okay, for these typical values. Now in the next few slides, what we want to do is we want to derive the expression for the current. How does this current vary as a function of time? Okay, so that's what we're interested in. Okay, so let's go do that. So one of the things that an inductor does in a circuit is to oppose variations in current to the circuit. Okay, when the switch is closed, current does not rise instantaneously to its steady state value. You saw that. Okay. All right. So what we want to do is, again, we are mathematically very sophisticated. So we see a system, and what we want to do is write down a mathematical model for the behavior of this system. So what we're going to do is we're going to close the switch. Okay. And now the current is varying with time. So okay, so at t equal to 0, we have closed the switch, and the current, you saw that is a function of time, and that's what we want to find. Okay. So, like I said, you guys are all experts at differential equations. You saw this system, and right away you write down an equation modeling this system. Well, how are you going to get that equation? Well, you know Kirchhoff's laws. Okay. And one of the Kirchhoff's laws says the sum of the voltages around a closed loop is what? The sum of change in voltages around the closed loop is what? Anybody remember that?
0.
So it says the sum of changes in voltage across all elements add up to 0 for a closed loop. Okay. So that's how, so this is the law we are going to use to come up with an equation describing the behavior of the system. Okay. So what we'll do is we'll start off here. We'll go across this element. There's the EMF of the battery. That's plus E. Then we'll go across the resistor. Current flows from a higher voltage to lower voltage. So you're flowing with the current. So it's minus ITR. And if the current is changing, if the current is increasing, this acts like a positive and this acts like a negative, and it's minus DLI by dt. So here's a differential equation that is modeling the behavior of the system. Okay, you saw that in a few milliseconds, the current goes to a steady state. This is not changing in time anymore. This term will go to 0, and E minus IR will be equal to 0. So within a few milliseconds, this differential equation changes to that. and I is equal to E by R. Okay, but we are picky and we are interested in understanding what happens in the first few milliseconds. And we have to use this differential equation. All right, so the behavior of this system after you close the switch is modeled by this differential equation, okay? And even Thai can solve this differential equation, okay? And this is the solution Thai came up with, okay? So how do I know this is a solution? Well, you learn various techniques to solve this, but to solve these differential equations, you learn to make better and better educated guesses, okay? But anyways, so here is the solution to that differential equation, and you can verify this. You can substitute that for I here, and you'll find that it is indeed a solution, okay? So you see, so this, if you plot this, that function will look like that, just like we had got in our simulation. Tau, that's the time over which things change, is called the time constant, and that's equal to L by R. That's equal to the inductance divided by the resistance. So smaller the resistance compared to the inductor, greater the time constant. So if you want things to change much more slowly, you want to have a low resistance and a high inductance. Okay. When t goes to infinity, this term goes to 0. And you see I is equal to E by R, like we said on our board. If for large times, di by dt becomes 0, I has acquired its steady state value, and I will be equal to E by R. Okay. So, and what do we mean by time equal to infinity? You saw that these changes happen over a few milliseconds. So 1 second is infinity. Okay, a few hundred milliseconds and stuff has already reached steady state value, and the current has already reached E by R. Okay, so current in an RL circuit builds up exponentially rather than instantaneously as for the purely resistive circuit. So what that bullet point is saying is, let's go back to, for a purely resistive circuit, the instant you close the switch, the current goes to its steady state value. With the inductor present, when you close the switch, the current rises exponentially like that. Okay. All right, so that was the meat of the chapter. Well, there's more stuff, but that was the most important thing. So I will pause now and let you guys ask questions. Okay, actually, before I pause, so let me summarize what we did again. Okay. So again, we were interested in how the current changes in the circuit when you close this switch. You saw in the simulation that the current rises exponentially to its steady state value, and we wanted the functional form for this current. So what we did was we modeled the behavior of this system by this differential equation. This differential equation models the behavior of this system. This is a first order differential equation, first order linear differential equation. Okay, and the solution to this differential equation is that. So that gives you the current as a function of time in this circuit. And again, let me emphasize that typically the time constants in these circuits are a few milliseconds. So stuff is changing over a span of milliseconds. All right, so I will pause now and let you guys ask.